Welcome class to today's interactive session. As land administrators and surveyors, you are tasked with managing critical boundary records and spatial GIS datasets. Today we are answering a vital question. How do you choose the right eye in the sky, meaning the correct remote sensing platform to accurately and cost-effectively map property boundaries, its monitor land use, and update our modern GIS land registries. Over the next 10 minutes, we will explore ground, aerial, and satellite platforms, complete interactive checkpoints, and design a master municipal cadastral strategy. Let us begin. By the end of this lecture, you will master three core learning objectives. First, you will be able to analyze platform trade-offs such as when to use aerial mapping versus ground and satellite platforms. Second, we will evaluate how the sensor platform combination impacts spatial resolutions and project budget constraints. And finally, you will design an integrated GIS strategy that combines multiple tiers of remote sensing data to run a modern or automated cadastral system. Let us establish our core theory first. In remote sensing, a sensor cannot simply sit on the ground next to a target if you want to a broad perspective. To collect and record the reflected or emitted energy properly, the sensor must reside on a stable platform that is removed from the target surface being observed. These platforms act as a stable base, and the choice of where to place this base determines what details we see and the image characteristics and our budgets. In land surveying, we categorize this base into three distinct type of platforms, which are ground, aerial, and satellites or outside the atmosphere. Students, please pause the video right now, read the scenario on the screen and decide which answer is correct. As a chief surveyor, what is your primary design constraint before selecting a platform? Welcome back. The correct answer is A. Because cadastral maps define legal boundaries, you need centimetric accuracy and high spatial resolution. A space telemetry or the global temporal resolution cannot resolve a fence line dispute. Excellent job. Let us proceed to explore our first types of platform, which is the ground-based platforms. Let us focus on the first, which is the ground-based platform. This places the sensor directly on their surface. We mount them on observation towers, tall buildings, or specialized vehicles like hydraulic boom trucks. Why do you need a ground sensor if their coverage is tiny? Because they act as our anchor, our baseline validation by taking precise environmental measurements and recording spectral signatures on site. We can validate and calibrate the larger sweeping datasets captured from aircraft or orbiting satellites above the surface of the Earth. Student, pause the video here. Imagine a local farmer disputes their boundary. A thick tree canopy has blocked clear visual boundary lines in your imagery. What do you do? Welcome back. The correct path is choice B. You cannot trust satellite data blindly when physical barriers like thick forest canopies interfere. By deploying ground-based GPS and sensors directly on the surface, you capture detailed local validation data to calibrate the boundaries. Now let us move on to the second types of remote sensing platform, which is an aerial platforms. Let us move into the atmosphere with the second, or it is an aerial platforms. Their tier includes traditional fixed-wing aircraft, helicopters, balloons, and crucially today, an automated surveying drones. These systems elevate our sensors above the Earth to dramatically increase the aerial coverage. Their absolute superpower is resolving survey bottlenecks in hazardous or very large areas. Instead of risking surveyors, safety, climbing steep cliffs or dense wetlands, aerial remote sensing let us safely map these zones with high precision from the above. Student, pause the video here. Draw a line in your notes. It's matching each project to its optimal platform based on what we covered. How do you balance coverage, resolution, and risks? Welcome back. Let us review. Mapping congested parcel boundaries requires an aerial precision. Localized canopy spectral data requires its ground-based validation, and monitoring national change requires satellite sweeping coverage. Now you are doing fantastic. Let's explore the third types of remote sensing platform. It is the space or satellite based platforms. Let us launch into space with the third platform, satellite platform. In space, sensors revolve continuously around the Earth, commonly carried by an artificial satellites or the space shuttle. Satellites are versatile, handling not just remote sensing, but its communication and vital GNSS telemetry for the precise coordinate positioning and navigation. However, the space mapping comes with massive engineering challenges. Satellites requires its completely remote ground operations, and their financial cost is an incredibly significant factor. And the historical record of satellite failures during launch or in orbit serves as a witness to the extreme complexity of space platforms. Student, pause the video here. See if you can fill in the missing blank A, B, and C concerning satellite project parameters and also their constraints. Welcome back. Let us reveal the answers. Blank A is its cost, blank B is telemetry, its location and navigation, and blank C is the failure, representing the high complexity of operating in space. Let us move to our the third tier comparative matrix to look at all these platforms in side by side. Let us synthesize our three platform tiers into side-by-side comparison matrix. This table is an invaluable cheat sheet for your surveying career. On the top, we have a ground-based platform operating at surface levels, delivering a millimetric detail, and they are low cost but excel at ground truth baseline calibration. In the middle, aerial platforms operate in the atmosphere, in delivering centimetric detail with centimetric details with drone imagery ideal for mapping contested urban property lines. And finally, the satellite platforms operate in space and delivering decimetric to metric resolution. Also, space missions are high cost and complex. They are replicable for regional GIS monitoring and nationwide parcel zoning. And how does a modern land administration office use this knowledge practically? We synthesize all three tiers into a powerful workflow inside our GIS. Step one, we deploy ground-based platform to validate local atmospheric condition and calibrate our physical sensors. And step two, we fly high-resolution surveying drones to map dense neighborhoods or steep hazardous terrains where the physical surveying is dangerous and also if it is impractical. And step three, we feed satellite data directly into our land information system to track regional zoning and environmental change when on a massive scale. this is how you run a modern automated cadastre. Student, pause the video right now. Evaluate these three final emerging approaches. Which one will you recommend to the land ministry? Welcome back. The correct technical choice is approach C, an integrated multi-user strategy leverage that best qualities of each platform, ground-based calibration secures accuracy, aerial system map its hazardous or dense zone safely, and satellite orbits monitor the regional trends. You are officially ready to run a modern professional cadastral mapping department. Let us wrap up today's masterclass. To summarize our session, first, stable platforms are foundation for accurate remote sensing. Second, you must balance spatial resolution, coverage, and cost when choosing your mapping system. And third, ground sensors play a vital calibration role. And finally, satellite systems offer a powerful sweeping GIS maps, but carry high cost and complexity. Keep studying, review this reference, and prepare for our upcoming lab exercise. Thank you for your active participation today, and see you in the next lecture. Thank you very much.